went a little out of order in terms of what I was going to cover. But so we were talking about two-level systems, and I hope it wasn't too wonky how I got. I just didn't quite finish it. But now, let me remind you that we were doing. We were just solving the eigenvalues of a 2x2 matrix. Now, you learned how to do that. You learned about matrices in high school. Eigenvalues, okay, maybe you learned that here. But a 2x2 matrix, you know, eigenvalues of a matrix. Remember, I think I introduced that to you in your first or second problem set. So what the heck could we have possibly learned now compared to the first week of class, right? Well, it was in the interpretation, right? So there was a Hamiltonian for one species, like a metal, and that metal has, let's say that's like the energy of that orbital, and then I drew a carbon monoxide orbital, a carbon monoxide ligand that was going to interact with that metal, which is a very common carbon monoxide. It's kind of crazy. Carbon monoxide, it's kind of dangerous, right? It's pretty dangerous, but it's commonly used in inorganic synthetic labs because carbon monoxide is a good ligand in here. I'm very unprofessional not to redraw that. And notice I'm drawing even symmetry, which is going to match quite well with the CO orbital. Remember that phase of an orbital is like plus minus, so that's important. They have to line up. Okay, so again, when it comes to a 2x2 matrix, it's like at this point this is quite literally infantile. But what happens is where the magic is when you do something like add them together, and so you get this. Now again, the eigenvalues are, I don't need to tell you what they are, right? I mean, you've done this enough, but then what we did was we then allowed these two species to come close together, so there became a bonding relationship, and we said that there is a coupling between them that looks like this. So this is as the two species become closer together. Okay, so what we were able to do there is, and Professor Trineri, who I think almost all of you are going to be in his class. Let me continue writing over here. It doesn't quite mesh with this over here, but I can't resist. We're going to have a mixture of these two states. These two states are going to mix, and that's due to off diagonal elements. And again, you may recall that I kind of pushed you to see whether you understood that about matrices, that only these states mix if there's off diagonal elements. And anyway, Trineri, whose class will be in, I think almost all of you, and that's a very good thing. If you're going to take, if you need spectroscopy, you want to take a class with him. Bluesec I've also heard very good things about. She's just not scheduled to teach it. Okay, so one thing I kind of made a mistake was, well, not a mistake, it just may have been confusing. So you're going to have two energies for this new matrix, and you know you can just plug this into MATLAB. You can solve the symbolic, or you can do it here. Trineri pointed out that I accidentally switched to the generic eigenvalue, lambda, right? So whenever you see an eigenvalue in the matrix, you use the letter lambda. You know, if you've done this again before, you end up with a quadratic equation when you solve the determinant. Again, now remember that it's just a math theorem. It's just a math theorem that the determinant of the Hamiltonian minus the identity matrix of eigenvalues. Well, what I'm doing is I'm solving this. That's what I'm really doing. And I'm solving this for lambda. For this equation to work, for this times that to equal an eigenvalue times that, for the eigenvalue equation to work, the determinant of the Hamiltonian minus the eigenvalues has got to be 0. And this ends up being a way to solve the eigenvalues. And again, I've accidentally equated, I've got e plus or minus into the lambda. And of course, the reason that you have two eigenvalues is that you've got yourself a quadratic equation when you solve this. And again, you've done this. I don't know what I'm talking about at this point. Let's see, then we solved e plus minus. I'm going to rewrite that. And then what we did was, with e plus or minus written, so let me remind you, so the order of operations is to solve lambda, which is really e plus or minus. Again, there were two lambdas because of because it's a quadratic equation. And the next thing was to solve the coefficients of expansion. Sorry, I was writing kind of small there, it bothered me. So again, one equation with three unknowns, really. What's this, what's that, what's that? So it's always been kind of funky how eigenvalue equations work. I mean, they shouldn't be solvable, right? I've got two unknowns. It's one equation. Go figure. Well, I guess this is your other equation. And don't forget, this coefficient squared plus that coefficient squared is equal to 1. So that's actually why it works, by the way, because you actually have boundary conditions that give you more equations to solve this stuff. And I have to admit, so I'm posting the video now, and it's just an exercise in algebra, so let's not worry about it. But what you end up with is some, unfortunately, a little bit more complicated than you would have probably figured, based on, again, a simple 2x2 matrix. How hard could this be? And it's not hard, but this expression for the coefficients ends up being a little bit much. Okay, so there's C2. I'm sorry, CA2, CA1, and of course, if I was a little bit better organized, I probably would just plop open MATLAB and then just plug all this into MATLAB, and MATLAB would spit all this out for me. So, not to necessarily lose all our math skills, but I don't mind shortcuts sometimes, especially if we're just going to get bogged down in hideous amounts of algebra and that kind of stuff. It's got to be perfect, or the world might blow up. Here we go. Okay, so that's the solution to everything. Now, as for this is as far as I got last time. Now, as for what do you do with all this ink on a wall, right? That's all it means right now. And so, the way that this is commonly expressed, and again, this is where I was kind of panicking last time because I was just running out of time. But yeah, I only needed 5 more minutes, but I didn't have it. So the way that the results are commonly expressed, and I find this weird, but this is how people do it. So, so what you want to do is express the coupling as an angle. And I don't really know why. I mean, I tried not to do that last time when I was kind of rushing, but here's the expression. Your book, if you look at the two-level system chapter, which is, I would call it an intermediate difficulty. What you can do is express an angle in terms of the coupling and the energy difference between levels 1 and 2. Okay, now, this is the part I don't like about this. This isn't like, oh, where did this get derived? Nowhere. It's just, I'm just expressing it. Now, the reason is that you end up with this nice expression. Oh, sorry, CA1, CA2. CA2. Guess what? Psi. So there's that. Now there's also this thing, the difference, which is something I just, last time I just expressed the difference as, I just wrote it in this graph that I'm about to draw. And anyway, again, I'm just wrapping all this up. And I want to give a couple of examples of this. Remember, I called this an avoided crossing. And this is really important for so many things. So what I'm going to do is plot. Okay, the way this works is, if you check this out, E1 is, okay, so that's basically the difference, and then the average. The average is E1, 1/2 E1 plus E2. Sorry, E2. So this graph is kind of easy to figure out, is if you notice that E1 is average plus the difference, E2 is the average minus the difference, and yeah, that completely adds up. That's correct. I double checked it before class. And okay, so now that I have a little bit more time, hopefully this graph makes a bit more sense. Okay, so this is the difference between them, and so I'm going to draw a cross, and the cross, that was E1 and this is E2. Yeah, now what I'm saying here is I've got something and another thing, let's call that metal and ligand. And I'm saying, their energy levels of those orbitals, one can be higher than the other. I was being all specific before, but now I'm trying to be a little generic. So here E1 is greater than E2, and here E2 is greater than E1 energetically. Okay, with that information, you can now, and with the knowledge of, let me make sure I get this right. Yeah. Knowledge of the coupling energy. And you see how I did that? You see how I'm making this space equal to that? What you end up with is this kind of behavior, or E plus. That's the higher energy. Okay, I've got to start here. And the word for this is asymptotic, so it asymptotically. Okay. So again, what you see here in the thicker lines is the quantum mechanical result. This is what you get. Now you can see here, if E2 is higher in energy than E1, then the higher state, maybe this is like the anti-bonding state, this is the excited state, I don't know, depending on what you're really modeling. You can see it's mostly going to have E2 character, and you can also figure that out from here. And so of course the lower energy level is mostly, in my example, the metal. But if the situation was reversed, the metal was a higher energy state, then the higher energy state is most of the metal, right? With some admixture of the ligand, and that's why these curves don't exactly follow these straight lines. Anyway, I hope that's kind of intuitive. Okay, now again, I have to dramatically emphasize this. I know this is very meaningful to you right now, but these have to have the same symmetry, or they're not going to interact. And one thing you should all do, especially for those of you taking spectroscopy, you'll get some of it in class, but you might want to do some self-learning. There's this book called Symmetry and Spectroscopy, which is about group theory. Group theory, which is an analysis, a very interesting and easiest way possible to analyze the shapes of orbitals, because understanding orbital shapes it's like direct notation for spectroscopy. It takes most of the intervals, most of the understandings and calculations of spectroscopy, and turns them all into not symbols, but like what are called tables, character tables. And you can get most of what you need to know about spectroscopy of molecules and reduce it down to just looking at the shape of the molecule and looking at a character table, and then it'll tell you whether a transition is allowed or unallowed, if molecular orbitals mix or don't mix. So this is a very important thing to know. And again, I'm sure you're going to learn quite a bit about it in spectroscopy, but when I was a grad student, I just picked up the Harrison Bertolucci book, and I just read it on my own. It's a very well written book. Okay, so anyway, other things that are kind of important in this, now imagine that this is like a reaction coordinate. So here's reactants and products. See, a lot of things, this is a good model for a lot of things, kind of like how I mentioned harmonic oscillators are good models for a lot of things, more than just bonds. I will often see a very similar diagram where it's like reactants are over here and products are over here. Now the reason this is important is that these curves we call the adiabatic, and the solid lines here would be called the non-adiabatic potential surfaces. You're going to see this word a fair amount, and people never define it. You're expected to know it. Now this again, notice I said reactants and products, so I'm talking about kinetics. Okay, the adiabatic, so what people do is they will express how you get from reactants to products either using a potential surface that is non-adiabatic, which is crossing, or adiabatic, which is non-crossing. Now adiabatic in thermodynamics means a system like an expanding piston, that's what you learn first, is thermally insulated. So what the heck has that got to do with this? The answer is nothing. Right? Except adiabatic transitions are also very slow transitions. So like adiabatic reversible processes are equilibrium processes. Things happen in equilibrium, like a ice cube floating in ice water at 0 degrees, that's equilibrium, but over time the cube turns into a sphere. So things still happen at equilibrium, but they're slow. Now imagine that you're going from products to reactants to products very slowly. The molecules are going to follow this potential surface, right? Because they see it. But now if they're non-adiabatic, now here's the new definition for that word. It means that things are going quickly. So you can imagine that the trajectory just follows the straight lines. Now, when you solve equations, kinetic equations or whatnot, using either the adiabatic or non-adiabatic surfaces, you get slightly different understandings of what happens. Anyway, that is something you're going to see. That's what it means. That's what it is. So I just wanted to show you that. Okay, let me give you one last example and then we'll move on. And this one's really fascinating. I hope you see more about this. This is something a lot of people misunderstand. And every now and then some poor fool rediscovers this. But in fact, I even saw a talk about this not too long ago. Let's take a, okay, we're going to take a nozzle. And in here is a liquid. And out comes little droplets. Droplets, droplets. Okay. Now let's expand the droplet. And what happens is that you have, so here's a dye, and the dye will emit, so the dye will emit light. Of course, if I say H nu, that means light. What will happen is that the light will hug the circumference of the sphere here, let me do it this way. Okay. What happens is, here's the light ray. it bounces off the sphere due to total internal reflection, and it keeps doing that. It keeps going and going and going. So what will happen is here, let me represent that a different way. So what happens is total internal reflection, total internal reflection, total internal reflection, total internal reflection. Usually, I probably should have drawn more light rays, but okay. So that is called a. So I tried to draw that a little fancier here, but hopefully you can get the point. So this is called a whispering gallery mode. Now, in terms of optics, this is like the coolest thing ever, and lots of research groups do nothing but study this stuff. Light becomes trapped inside the sphere. So spheres are, a droplet is typically spherically perfect to a molecular level. So it ends up becoming the best optical cavity that has ever existed. It's technically a laser cavity. Laser cavities, if you think about it, I know you were taught as undergrads, it's two mirrors, right? And one is a high reflector, one's very polished, the other one's semi-polished, and that's where light leaks out. But really, what is it doing? It's allowing light to go back and forth many times. It's really a light trap. And that's when laser buildup occurs, because the light's trapped. This does the same thing. In fact, it actually does too good a job. Sometimes you can build, if you make one of these perfect, light never gets out of it. So it would be the most powerful laser that ever was created in the entire universe over all time, but you can never know it. Nothing's that perfect, okay? Light will scatter out of it. Okay. Now, for one, I'm glad for you to know that. This is actually what I did as a postdoc, so I can talk about it. But what you see optically is absolutely fascinating. So this is an example of really the highest level of quantum mechanics. One of these states is the molecule, the other is the light itself. Light molecules can interact like metals and ligands. And it's not hard for us as chemists to understand metals and ligands interacting in botany. I'm twice as old as all of you, but you don't even need to tell me anything. I just get it. Right? The electrons are going between them, and there's a bond. All right. But here, that's a molecule, and that's light. So what happens is this molecule has a mode, a laser mode, and the molecule, the sphere, the cavity has allowed frequencies like any laser, and the molecule emits at a certain wavelength that's just photoluminescence. So what happens is you can actually see if you do emission, if you make one of these droplets with a dye and you do emission, what you can do is as a function of sphere size, that would change the cavity mode. You can see, here's your molecule emitting photoluminescence, and here's the light that's trapped in the cavity mode. And as you change the size and they get closer together, what happens is, let's say that you're shrinking the sphere. You can do that by either making different sizes or letting the sphere evaporate. Eventually, it actually goes the other way. So it does this. So the molecule will only emit at the same wavelength. The molecule hasn't changed. But you'll see the cavity mode, due to shrinkage of the cavity, it'll get closer. That's just the cavity resonance changing. It gets closer, but then it backs off. It'll just keep doing that. Anyway, that's kind of a cool thing. And again, I do see, I was at a conference and I saw a big long talk just about this. Now, the reason that this works the way it does, by the way, is this is another word I'd just like to show you. I think I'm kind of blowing a lot of time on my trivia stuff. But again, I do want you to know some stuff that's current and modern. So if you look at a molecule like a two-level system, ground state and excited state, what happens is that the light inside of the sphere, which, by the way, you would do that by shooting of the laser, and tend to say, actually, another fascinating thing is you would have, use a laser to excite it, and then you would just have some kind of little fluorimeter that can catch the emission as the droplet drops. Just like light is trapped inside of it, you actually have a hard time putting light into it. So sometimes when people do this kind of work, you have to be careful about what kind of laser light you try to shine on it, because just like light stays inside of it, light can't get out, light can't get in. So sometimes you have a hard time exciting that little dye molecule that lives on the edge. Anyway, so let's assume that you got lucky in your laser, your very intense laser, got a couple of photons in here, and then it excited that molecule, and then you're able to see what happens next. So the ground state gets excited, because that's what happens when you excite things. But then comes that whispering, the whispering gallery photon came from the molecule, but it's trapped. So it comes back and re-excites the molecule. The molecule then fluoresces, but it fluoresces into the cavity mode. And so now the molecule is back in the ground state, but then literally the photon skirts around like a little skater boy, and it comes back. And then it just goes on and on and on. And so this is called a Rabi oscillation. It's also something important in NMR. If you need NMR, do NMR, you're going to hear that. And because this never stops, you end up having a situation where you have a Hamiltonian for light and a Hamiltonian for your molecule that end up adding, and then you're in this two-level system. Let's see. There's also something called Purcell effect. Purcell effect. Now, I see this quite frequently in optics, and what this is that intensity. So let's look at, let's have our eye. This is how you commonly draw molecular setup. So you're trying to describe your instrument. You have an eye for your fluorimeter in this case. And maybe this fluorimeter is time resolved. Many of them are. Now a dye would emit light usually on the order of about 1 nanosecond on its own, but inside of a cavity, it emits light into this whispering gallery mode, and that's when the light travels along the sides in like this total internal reflection ray diagram. When it does that, the dye emits faster. So that's in a cavity. So anyway, that's really kind of fascinating. So again, something that if you get into any high-level optics, quantum optics, you are studying this, by the way. So, okay, look, I kind of went off on a crazy tangent, but I just thought it'd be kind of nice every now and then to talk about some real high-level stuff that you see at conferences, so it's one thing just to present, oh, look at these two-level systems, another thing to tell you a little bit about the stuff you might see at conferences and whatnot. Anyway, yeah, interesting. Okay, all right. So let's drop all this and do something completely different. Because actually, I guess I kind of feel like talking about this because I hope this is kind of fun. And whenever I see talks at conferences about whispering gallery modes and Purcell effects, quantum electrodynamics, the graphs and figures, it's usually like really, it's an interesting seminar, very visual. Anyway, okay, I'm off on a tangent. So let's switch gears. Now, as I was mentioning before, if you have a metal ligand complex and you want to know its predicted spectra, you would use programs like Gaussian 16. Every 4 or 5 years they come up with a new version. They name it based on the year. There is GAMESS, G-A-M-E-S-S, from Iowa State. That's a big one. I think that was the first one. QChem. Then some newcomers are like VASP, Quantum Espresso. Anyway, packages that were written by really people who are way better programmers than me. And you would plug in your molecular specifications, details on the computational method, which really requires a separate class. That's not really what I'm covering. And outspit the predicted absorption spectrum. That would be like, it can do vibrational spectrum, it can do absorption spectrum, which is a bit more of a complicated calculation. Whoop-de-doo. Okay, again, that's a whole nother thing. The calculations you're going to do, because you're going to do them on your homework, well, I'm going to show you what you can do. These are going to be good for really more like more complicated vibrational potential surfaces. You cannot really do electronic structure like this, except you could do like a particle in a sphere calculation if the particle is an electron. That actually isn't a bad model. You may recall, we talked about this a while ago when we were talking about particle in a sphere. That's actually a reasonable approximation for a semiconductor nanoparticle. And you even did some calculations on that. So you're actually going to repeat that using the methods I'm about to show you, because you can describe way more complicated structures using the methods I'm about to show you. Okay, now the way it works, and this is called finite difference. Finite difference method. FDM. Now, if you got some engineers in the back, you guys heard of FDM? Yeah. You know how to do it? You've heard of it, yeah. COMSOL is FDM, I believe. I think it's entirely FDM. So now you're going to really know how it works, by the way. This is like one of the coolest things I know, by the way. You can solve crazy things with this, and you can type up the code in a matter of minutes. Okay, here's the idea. And now you're already used to this. Let's get a wave function. Let's do a particle in a box. Now imagine you're doing it with MATLAB. You know, you've got points, for I equals 1 to 100. WF of I equals cos, I times pi over, right, you've done this. Now, let's think about these as finite points. Okay, that's not the best that you can cosine, but that's a sine. I anyway. Okay, so hopefully you can imagine this. Now let's think of it more like a table. Oh, well, a table of numbers, a column vector, if you will. Maybe it could be 100 or 1,000 or 10,000. Okay, now if you can make this intellectual leap, which I could contend is not particularly difficult, can you do this? Now again, you've seen Hamiltonian matrices. You've seen wave functions equal to an eigenvalue times the wave function. I mean, again, you did quite a bit of this with spin. That's Sx, that's whatever, right? Now, what I'm going to do is we're just going to up the ante and make it a little bit more complicated. So maybe this is particle in the box, there's 1,000 points. MATLAB has a vector, technically it's a vector. Okay, eigenvalue equation is not particularly mind-blowing at this point. All you got to do is basically have a matrix that, for the most part, let's just start simple. Let's just do kinetic energy. Let's say that there's no potential surface. Let's say the Hamiltonian's kinetic energy, which is a double derivative, right? It's just p squared over 2m. Mass is a constant, no problems with constants. The operator is really the double derivative. So can I write a matrix that takes the double derivative of that? How would I take the double derivative of a table of numbers? Huh? Mind-blowing? Possible, impossible? Why am I talking about it? So that's kind of a stupid question on my part. Well, now let's visualize it so that you kind of, you might get a little bit lost in the mathematics that we're about to do. That would be kind of fair. So you might get a little lost in the mathematics we're about to do. So just remember this. Okay, so let's look at this thing. All right. So let's take so I have a table of numbers. I created them myself from I equals 1 to 1,000, cosine I pi over 1,000. Okay, so I have this table of numbers. If I take the derivative of it, okay, well, it looks like the derivative is positive. Okay, positive. After 2 points, its derivative there is 0. Then it turns negative. Like that. Okay. All right, we'll take the derivative of that. What does that look like? Actually, yeah, let's take the derivative of that. Okay, so that's negative. So we'll assume that it's, if I had drawn more points here, if I had more points, it actually would have kind of looked like more like this. Okay, so the derivative here would have been 0, close to 0, and it starts out 0, then it gets really negative, and it goes back to 0. Again, I didn't draw that super well. Anyway, and you can also see, as I'm kind of struggling to draw this well, you can see why the computational method it has some inherent approximation thing. Okay, now if I take that times minus, look at that. Is that the same as that? Is it? Looks the same. Maybe it's scaled. Just scaled differently, probably. What do you think the scale is equal to? Something operated is equal to itself times what? You heard of that before? Something operated on is equal to itself. It's just scaled by, yeah, the eigenvalue. Right, so if this is the Hamiltonian, if this double derivative is really the Hamiltonian, notice I'm multiplying by minus. Well, if it's minus h bar squared over 2m, whatever I need to do to scale this back to that times minus h bar squared over 2m is the energy. Now I have the energy. Right? So again, all I'm doing here is I'm just showing you, you can take a table of numbers, I can look at it, just look at this, I can calculate the derivative of that. How do I do that? Let's do a close-up. Point, okay? Well, here is the delta x. Delta x moves over by 1 unit. Now, you might, of course, need to keep track. You can do this without worrying about what the x-axis really is, but you should know what the x-axis really is. You're modeling this, whatever this is. It's your model. You should know what the x-axis is. So maybe this is 1 nanometer or 2 nanometers or 1 Bohr, that's 2 Bohrs, 3 Bohr. I don't know. You tell me. But I can tell you, you can actually do all this modeling and you can kind of actually drop that part. And you can't drop this part. You gotta know what delta y is. And the slope, of course, is delta y over delta x. There you go. Now, and then you do this calculation, and then that's the point here. And you do that with all of your points. Now, one thing you should notice is I've used 2 points to get 1 point over here. So this method is lossy. You're losing information. Because 2 points have to be turned into 1 point. So when I drew the same number of points here and the same number of points there, I had to do something a little bit weird to get that, to do that, which isn't really correct. Anyway, and then if I'm going from here to here, I had to have shaved off another point. So to go from a signal to its delta derivative, somewhere you probably lost 2 data points. Again, just because a slope is defined by 2 points, and the slope is a single number. So there's that. That's really not a big deal. All right, next thing, keeping track of time. Okay, now can anyone think of a better way to do this? Don't you think, is it possible to have the third number? So what if we, mentioning this loss, I don't know if I want to center, all right, so I'm calculating a slope from these two numbers. Where do I center the, so when I drew this graph, where did I center it? Did I center it at points 1 or 2? So you're saying center it in between. That's actually would be reasonable. Okay, but then, okay, MATLAB. Now think about doing this with MATLAB. That point is not defined, right? Because your index goes 1, 2, 3. Not, you know, it's literally impossible. You know, if you say MATLAB, what's position 1.5? It says, no, I have to have a whole, I have to have a, you know, an integer. Okay, so that was actually a good move, but you literally can't get MATLAB to accept the number, the slope as being in between. So you have to choose when you create this. You have to choose to write the slope as either being at point 1 or point 2. What do you think? Which one would you pick? 1. Okay, I can tell you 2 would be reasonable. Now, if you choose 1, notice that you're going to lose the last data point, right? Because by definition, that last calculation was placed on the n-1 data point. So there's nothing to generate the nth data point in terms of the slope. Okay, and if you do point 2, obviously you shaved off the first data point. So again, you can see how you lose a little bit. Okay, now let's say you did choose to use point 2. I contend that's actually the better choice. Do you know why? Where do you calculate the slope? Which one do you calculate the difference of to get the slope? Because now you can look at the data point before it or the data point after it. Which one do you choose? Now again, I said there's an inherent advantage to using point 2 as opposed to point 1. And I'm giving a big hint. Which one, the forward or backward one, do you use to calculate the slope at point 2? Which one, left or right? Or is there another option? Now again, I'm saying instead of calculating the slope here and using this delta x over delta y, I'm saying begin your derivative plot here. But now my question is, because you have 2 data points. What's that?
Like average, what the slope?
Use both data points?
No, okay.
Use both data points. Either is valid. You see that? Using this point to calculate the slope is just as good as, you know, looking forward is just as good as looking backward. The cool thing is you have 2 numbers to work with, and so you would calculate both and take the average. So my point here is that when it comes to calculating slopes from data, calculating derivatives of data, you can get kind of fancy with this. You might even be able to optimize a mathematical routine to do that. Okay, with that said, let me point out the way you're going to do that. And what have we got? 1 minute left?
1 minute.
Okay, now the way you're going to do that is you're going to calculate the slope. And notice I did derivative. So you're going to calculate the derivative of a function. The way you do that is a Taylor series. You're going to calculate this as a function of the point behind, a function of the point you're at, because that's obviously important, plus a function of the point in front, where H is 1. So this means point behind the current point you're trying to calculate the derivative of, and the point in front. So just like I calculated, you know, this minus that divided by h, which is your delta x, and then the same here. So again, one person said calculate both slopes. Notice that you can do that with this. If this was like 2 and that was minus 1, then this is this minus that, which is the slope. If this is 2 and that's plus 1, then that's technically this one here. Anyway, so, sorry, that's not quite right. But anyway, I think you get my point. If you know what A, B, and C are, you can actually use this formula to calculate the slope at the middle point, incorporating information with what's in front and what's behind. And you can also do this with the double derivative. And anyway, so H can be 1 for the data point or grid spacing. Now, what I mentioned before, I said you can do this finite difference method either just saying I've got data point 1, data point 3, or 1 nanometer, 2 nanometer, 3 nanometer, or 0.1 nanometer, 0.2 nanometer, 0.3 nanometer. You can use any representation you want, but let's go with 0.1 nanometer, 0.2 nanometer. Let's make it real because you can't go wrong. Okay, so anyway, as I develop the algorithm next time, we're actually going to work with 1 at first, just to make it easy, and then we're going to later use the grid spacing as defined by your problem. And what we're going to do is we're going to optimize A, B, and C to give the best slope given that you have this finite, the technical term is discrete data set. You have a discrete data set. A, B, and C will be optimized to give us the best possible slope with that discrete data. Okay, sorry, I went over.